AP Calculus section 4.1. Now the moment for the antiderivative. So instead of doing differentiation, we're going to be doing antidifferentiation. Now the antiderivative is also referred to as the integral. And I'll try to use those interchangeably so that you'll be able to know when you see antiderivative, it's actually the integral. Now, what that means is that when you take the derivative of a function, okay, so you have the derivative of f of x, it's f prime of x. Well, if you were to take that integral of that derivative, you're going to get back to where you started. So it's you cancel out. So a derivative and an integral cancel each other out. So we're going to be going backwards. I gave you the original function, you gave me the derivative. Now I want you to look at it as if it's a derivative and take it back. So let's look at the derivative of all three of these functions. These functions are all different. So when I take the derivative here, I'm going to get 6x plus 6. Well, when I take the derivative of this one, I get 6x plus 6. When I take the derivative of this third function, yep, you guessed it, 6x plus 6. Now, all of these functions were different, but all their derivatives were the same. What was different about these equations? The constant. There wasn't even a constant here. So what that means is that when we integrate, we'll be able to get back to the original function within a constant. Okay, so we'll be off by a constant every time. So if I were to ask you to integrate 6x plus 6, that answer is going to be 3x squared plus 6x plus some constant. I don't know what that constant is. In order for me to be able to tell you exactly which equation you're talking about, you're going to have to give me a point on the graph. So unless they give us a point on the graph, we will not be going back to the original equation. Okay. Now, what we have here are power rules. The derivative of a power. Let's see. Let's do this in the pretty color. So when we took the derivative, we brought the power down in front. Let's just write it. So the power rule for differentiation, you bring the r down in front and you subtract 1 from the exponent. Now we're going to be integrating or anti-differentiating, and they're going to give us x to the r, so it's a power rule. We're going to add 1 to the exponent, divide by that same value, always plus c. That plus that constant, we don't know what it is. Now, you might have noticed that when I wrote this out, I put a dx in there. That dx is there so that you know which variable you're changing, which variable's power is changing. Because let's face it, we had an x and we had an r. How do we know r isn't our variable? That's where that dx, that differential, remember that means your change in x, so that means that's the guy we're changing. That dx is very important. Make sure you're writing it each and every time you're doing an integral. So just like the power rule with derivatives, we're going to make sure that we have it written in power rule form. So x squared is ready to go. We're going to take the integral, so we are going to add 1 to the exponent, divide by that same amount, add our constant that we don't know what it is, but we will get a point eventually, and then we'll be able to find out exactly what that constant is. So number 2, I have to rewrite it first. The 5th root of x squared is x to the 2/5. Never write your integral without your dx. So when I add 1 to the exponent, that's going to be x to the 7/5 divided by 7/5. But when I divide by 7/5, that's multiplying by 5/7. I still have that plus constant. Okay, so even if it's a variable, you're adding 1 to the exponent, dividing by that same amount. If it's a fraction, please make sure that you flip and multiply so that you get that all simplified. Number 3 here, I've got to simplify that again, so that's x to the -5th dx. Add 1 to the exponent, so that's -4 divided by -4 plus c. Don't think, oh, well, I'll just wait till the very end to put that constant on. You do that, you're going to forget. Always simplify. He's coming down in the bottom. I'm going to keep my negative on the top. I don't like it on the bottom. It creeps me out. I don't know why it creeps me out. It just does. So we've got our power rule for integration, just like we had a power rule for differentiation. We have a couple rules here for our properties of integration. With integration, a constant can be pulled through the integral. Okay, so if I'm taking the integral of 7x dx, that's the same thing as 7 times the integral of x dx. That coefficient is just along for the ride, kind of like with the derivative. Anything that you'll be multiplying or dividing, you're going to make sure that you do that as well with the constant, with the coefficient, sorry. Now, if you're taking the integral of things that are added or subtracted, you're going to take the integral of each part and add or subtract it together, whatever you had there. Well, that's kind of a no-brainer because you know you're not going to have just one term in your function. So let's look at what that's going to look like on number 4. You've got 3x to the 6 minus 2x squared plus 7x plus 1. We're integrating that. I would suggest you integrate and then simplify in your next step if you need to. So 3x to the 7th, we're adding 1 to the exponent, dividing by that same amount, minus 2 times x to the 3rd over 3 plus 7x squared over 2. It's really kind of easy if you think about it. Now, right now, this was an x to the 0, so I would have 1x to the 1 divided by 1 plus our constant. Okay. And of course, there's nothing here that I can simplify. Remember that 3x to the 7th over 7 is just 3/7 x to the 7th. I don't want you to get hung up about the notation or get confused and think, oh my gosh, that's a product and a quotient rule, because it's not. Okay. So there's our final answer. Now that one was nice because it was all nice and pretty. Okay, we're going to save number 5 for just a moment. Okay. So now, remember, we could not get back to the exact equation unless they gave us a point. So guess what? They're giving us a point. We are going to take the integral of 6x to the 2nd dx. Remember, you've got to put that differential in there because we are changing the x. They want the exact equation this time. So we're going to integrate. So that will give us 6x to the 3rd divided by 3 plus c. Okay, and this is what our f of x is equal to. So f of x is equal to 2x to the 3rd plus c. Then we're going to put our values in. We're going to put 0 in for the x. So 0 is going in here for the x. -1 is going in for the y. Remember, f of x is our y. So that'll be -1 equals, 0 plus c. So c is -1. So my full-blown equation exactly is 2x to the 3rd minus 1. The only way we're getting back to the exact equation is if we have that point. Okay, so here we've got to integrate our 6x minus 8x to the 3rd. Don't forget your dx. So that's going to give us, if we take 6x to the 2nd divided by 2 minus 8x to the 4th divided by 4 plus c, that is now what f of x is equal to. Okay, go ahead and simplify. Don't try to do too many steps at the same time because that's when you get all tangled up in it. And we don't want to lose points for our algebra. We're going to put 3 in for our y and 2 in for our x's. We're going to find out that c turns out to be 23. So our final equation, 3x squared minus 2x to the 4th plus 23. Okay, unless they give us a point, we cannot get them back to our exact equation. But if they give us a point, we can get them right back to where they belong. Okay, now we skipped that one example because it was a trig function and we haven't kind of gone over the formula for that yet. We shall. Remember that integration is anti-differentiation. Every trig function had a derivative, but remember, their derivatives were sometimes different. For instance, the derivative of sine was cosine, so that means I'll be able to find the integral of cosine. The derivative of cosine was negative sine, so I'll be able to find the integral of sine. Now we get into a problem. The derivative of tangent is secant squared, so I will only know how to find the integral of secant squared. At this moment in time, I do not know how to find the integral of tangent. We just don't know yet. Don't know yet. Okay. Now when we took the derivative of cosecant, we got negative cosecant cotangent. So we don't know how to find the integral of cosecant. We don't know how to find the integral of secant because remember the derivative of secant is secant tangent. So we only know how to find the integral of secant tangent. And we also don't know cotangent. So the only two trig functions flat out that we know how to integrate are sine and cosine. After that, we know how to integrate secant squared, cosecant cotangent, secant tangent, cosecant squared. Now you can see that one of the problems we're going to encounter is the fact that the derivative of sine is positive cosine, but the integral of sine is negative cosine. So we're going to have to be very, very careful. Okay, so now we're going to do some trickier examples. Okay, now when I'm looking at number 8 here, just like with derivatives, if you can simplify it, you need to do that. Just to kind of let you know, there isn't a quotient rule, there isn't a product rule for integration. So if you've got a quotient, you are going to have to find that quotient by yourself. So you're going to have to divide on your own. So that's what I get when I divide on my own. Then I'm going to take my integral, so t to the negative 2 divided by negative 2 minus 2t plus c. These are called indefinite integrals. They'll all have that plus c unless they give you a point on that graph. So if you have two things being divided, you're going to have to divide that on your own. There isn't a quotient rule for integration. There's also not a product rule, so you'll have to multiply that out. If you FOIL that out, you're going to get a nice, pretty product. And you'll take the integral of that. So 2x to the 3rd over 3 plus x squared over 2 minus 28x. Don't forget the plus c, because I can guarantee when I'm grading I won't forget it. Oh, sliced right through the c. Okay. Now let's go back to that one trig function that we skipped. Okay, let's go back to number 5 here, because we've got the nice, pretty easy ones. So when you're taking the integral of 4 sine, that's 4 times the integral of sine. Well, the integral of sine is negative cosine, so that's going to be negative 4 cosine. The integral of 2 cosine is the same thing as 2 times the integral of just plain cosine. That coefficient's along for the ride. So that'll be 2 sine of x plus c. Well, they're not all that easy. You'll have trig functions that look like this. Remember your trig identities. I think we should have some quizzes. Alrighty, so we've got a double angle here. I want to use my double angle formula for sine. to redo this, to simplify this. So that nasty looking thing, 2 sine of 2x divided by cosine of x, is really 2 times 2 sine of x cosine of x. Cancel what you can. Okay, that cosine cancels with that cosine. So really, we are just being asked to find the integral of 4 sine. Well, now it's a very pleasant problem. The integral of sine is negative cosine. The integral of 4 sine would be negative 4 cosine. It's a coefficient. Don't forget the plus c. We ought to make a song. Somebody who is a good singer, make us up a song. Well, cosine squared. This one's a tricky one because remember there are only certain things we can take the integral of. We can integrate sine, cosine, secant tangent, cosecant cotangent, plane secant, plane, wait, no, not plane secant, secant squared, and cosecant squared. So those are the only thing we can integrate. So when I'm looking at sine over cosine squared, I'm thinking trouble. Now, when we see our cosine squared, it might be a good idea for us to split that cosine up. By splitting it up, sine over cosine is tangent of x. Kind of merge those. Tangent of x. 1 over cosine is secant. And look at that. We have secant tangent, which we know how to integrate. That's secant. Now you can see how incredibly tricky these trig functions are going to be. They're going to be next to impossible if you don't know your identities. We can integrate sine by itself, cosine by itself, secant tangent, cosecant cotangent, secant squared, cosecant squared. That's all. So we have got to simplify these as low as we can go. Now, using that same method, I want you to try number 12. So pause the video and then see what comes up. Okay, so pause it. Try to do it. Alrighty, so after you unpause, 1 minus cosine squared is sine squared. Now this problem is very much like what we just did. Split up the sine. We are unmultiplying, factoring. Sure enough, we get our cotangent of x times cosecant of x, which we do know how to integrate. It's negative cosecant plus c. Okay. Now pause the recorder on number 13 because I want you to try that one yourself. So pause it, see if you can come up with it. Okay, hopefully you've tried it. You're bringing it back on. Sine squared plus cosine squared is 1. The integral of 1 is x plus c. Yay! Hopefully you tried it. We're pleased with the results. Now, they've kind of switched things up on number 14. They have given us the second derivative. They've given us a point on the first derivative and a point on the original graph. Kind of tricky. Well, all we're going to do there is integrate a couple of times. We've got to integrate the second derivative to get to the first derivative. So when we do that, we're going to have x to the third over 3 plus c. But wait a minute, we have a point on our derivative. We know that when we put 0 in for x, and 0 cubed over 3 is 0, we get 6 for y. So c is 6. So here's my first derivative. Exactly. To find the original function, let me change colors. To find the original function, I'm going to integrate my derivative. Don't forget your dx. When I integrate that, I'm going to have x to the fourth over 3 divided by 4, which is just 12, plus 6x to the 1 divided by 1, same thing, plus c. I know that when I put zeros in for the x's, my function equals 3. So if you put 0 in for all your x's, c is 3. We rewrite it all nice and pretty. Also let people know what it is that this represents. It's our original function, which is what they wanted us to find. Okay? Thank you for coming to the show, watching the show. I'll see you at school tomorrow.